In this section, we will go over the different edge computing scenarios so that you have an understanding of what edge computing is to build the foundation for this course. Since this is a course in the Microsoft Azure AI track, I want to introduce you to the edge computing from Microsoft's point of view. Over the past few years, Microsoft has been using the tagline Intelligent Cloud, Intelligent Edge. Let's define those two terms. Intelligent Cloud is ubiquitous computing, enabled by the public cloud and artificial intelligence technology, for every type of intelligent application and system you can envision. The Intelligent Edge is a continually expanding set of connected services and devices that gather and analyze data, close to your users, the data, or both. Users get real-time insights and expertise delivered by highly responsive and contextually aware apps. At the time of this recording, Microsoft has a list of services and scenarios for the Intelligent Edge. These services cover a wide range of use cases. There are listings for the Azure Connect DK, the HoloLens 2 for mixed reality. There's a listing for new apps for Dynamics 365. There are listings for Azure Sphere, drones, industrial assets, Azure Data Box Edge, and Azure Stack. In my opinion, these listings are mixed. Some are edge computing and some are products that relate to or interact with Microsoft Azure. You should see this as a warning that the marketing around the Intelligent Edge will list products and services that are not, in my opinion, edge computing. Beware of this for all companies that market their edge products. Instead of trying to describe edge through products and solutions, let's group them into tiers to understand not only how edge relates to the cloud, but how edge can relate to other edge implementations. The largest edge implementation would be a data center not hosted in the public cloud. This can be a private cloud, hybrid cloud, or any data center. For the data center to be considered edge in this scenario is for it to have interoperability with the public cloud. This can be as simple as shared networking or shared services between a public cloud and a data center, all the way to a seamless public-private cloud hybrid. The next tier is a server. Not every server is an edge device. If that server is acting as a data store where the source of truth is in the cloud or that server's functionality is controlled by a public cloud, then it's an edge server. A real-world example of this would be the server in my office. It syncs files with Azure and acts as a local copy of a cloud-hosted database, then it's considered an edge server. There isn't a clear separation between what is an edge server and what is an edge gateway. The most defining feature of a gateway is that there are downstream devices supported by the gateway. There could also be gateways supported by a gateway, but to avoid showing you a picture of Russian dolls, understand that gateways have downstream devices that use it for connecting to a private or public cloud. An example of an edge gateway would be a protocol translator for Modbus or SCADA systems that allow those systems to interact with a private or public cloud. Another example would be a system consisting of multiple camera feeds where a gateway processes those feeds before pushing the data to a public or private cloud. Finally, the last tier is that of a device. Devices can be any single instance form of computation. It could be a mobile phone, smartwatch, microcontroller, camera, or many things. There isn't really any designation of a device and an edge device because any device can become an edge device when it connects to a public or private cloud through any of the other tiers. There are a number of different edge scenarios. In fact, we could dedicate an entire course to just exploring the use cases for edge computing. Instead of looking at the possible scenarios, let's take a look at some of the more common ones. If you have a solution that needs to be real-time or close to real-time, then latency becomes a factor in how you process data. In a scenario where a device is processing incoming sensor data to detect if there is a dangerous situation, sending all of that data to a remote processor could lead to situations where the dangerous situation is not discovered in a timely manner. It could be caused by unexpected latency over the public internet or a slower than expected process on the back end. Instead, the sensor or supporting locally connected hardware can run the logic to handle the dangerous situation without any delays from utilizing the internet or your cloud. Looking at a similar scenario, except this time, let's expand the sensor data definition and say it's video data. Imagine a scenario where there are multiple camera feeds that need to be processed to detect a dangerous situation. The video streams may not be able to stream all of their data to a remote processor due to bandwidth. Video data can be very large and take large amounts of bandwidth to stream. We hear about large video streaming platforms having trouble due to load. Uploading your own video data can be quickly hampered by lack of bandwidth. Instead of streaming all the video streams remotely, the video data can be processed locally, and the information discovered through that processing can be used upstream for either more advanced processing or decision making. In the previous two scenarios, and in many other cloud architectures, there is an assumption that the cloud is always accessible. There are plenty of use cases where an application requires offline support so that the edge processor can continue to function. In the first scenario, we discovered a dangerous situation and handled it in a timely manner. When an edge processor gets disconnected from its backing cloud, it still needs to be able to handle the dangerous situation. For an oil pump that detects pressure and needs to be shut down if there's a sudden drop, the business would suffer if every time the backing connection was lost, it had to stop pumping, or it had to pump in a situation where it could damage itself. Instead, the pump can run locally and handle the detection and take action without communication with the backing cloud. Speaking of oil pumps, not all pumps, or devices like pumps, were built with Wi-Fi, LTE, or Ethernet in mind. They were built with a different type of connectivity. It doesn't matter if it's a Modbus, SCADA, OPC UA, Bluetooth, or many other communication technologies. If it cannot utilize TCP/IP, then it will likely need a translator to connect to a public or private cloud. This can fill a number of different architectures we will discuss later in this module, and serve to solve multiple different scenarios. Different from the connectivity issues we have discussed so far is the ability to utilize existing resources. If you build a mobile phone app that can detect the type of food in a picture, then it would be logical to have the phone process the image rather than sending the photo off to be processed in your cloud. By having the phone do the processing, the CPU time is offloaded onto the device instead of your cloud. If you don't have to worry about any latency, bandwidth, offline support, or connectivity issues. Also, to utilize previous infrastructure investments, companies need edge solutions to integrate their utilization of the public cloud with their existing infrastructure. Finally, there are situations where companies do not want to expose their intellectual property to the cloud. Instead, those companies want to run their IP on their own infrastructure. Edge solutions provide a way for companies to own the pipelines that utilize their technology without running it on another company's hardware in a public cloud. In the next section, we will look at architectural concerns when implementing an edge solution.